Another way we can use the remainder theorem is to test whether a given rational number is a zero for a polynomial. To do this, we'll be using the rational zero theorem to help us narrow down the number of possible zeros that we can have. As it turns out, the rational zero theorem is going to characterize how the zeros of our polynomials are going to look like if they're a rational number. So if the polynomial f of x has integer coefficients, then every rational zero of f of x has the form p divided by q, where p is a factor of the constant term a sub 0 and q is a factor of the leading coefficient a sub n. Again, this theorem is going to be useful if we want to completely factor a polynomial and we don't know what the zeros are. This allows us to find possible zeros and then use the remainder theorem to check to see if they correspond to any factors of our polynomial so that we can divide it and simplify it. Let's go ahead and apply this theorem and find all possible rational zeros of a given polynomial. So all possible rational zeros of a given polynomial are going to be able to form p divided by q, where again p is a factor of negative 10 divided by a factor of 3. So the factors of negative 10 are given by plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. The factors of, in this case, 3, are plus or minus 1 or plus or minus 3. So we'll start off with holding constant our denominator. We'll have a plus or minus 1 here. And so up top then we have either 1, 2, 5, or 10. And on the bottom again we have a plus or minus 1, plus or minus 1, and a plus or minus 1. And now again we're going to go ahead and keep our denominator constant, and the other possible zeros are going to be given by plus or minus 3, where we're dividing 1 by plus or minus 3, we're dividing 2 by plus or minus 3, we're dividing 5 by plus or minus 3, and we're dividing 10 by plus or minus 3. So simplifying this, the potential zeros are going to be given by the following: either a plus or minus 1, a plus or minus 2, a plus or minus 5, or a plus or minus 10, which come from this first row here. And then we're either going to have a plus or minus 1 divided by 3, a plus or minus 2 divided by 3, a plus or minus 5 divided by 3, or a plus or minus 10 divided by 3. So again, let me reiterate that these are zeros of our polynomial, but only potentially. We don't know if they actually correspond to zeros. We would have to check this using the remainder and factor theorem. In the next problem, we want to find all possible solutions of a given polynomial equation, and we'll be using the rational zero theorem, the factor theorem, and the remainder theorem. So in this problem, we want to find all the solutions of x cubed minus 3x squared minus 25x plus 75. Or in other words, we want to find all the zeros of this polynomial. So in the first part of this problem, since we don't know any of the factors, we need to go ahead and use the rational zero theorem. This will give us a potential list of zeros where we can use the remainder and factor theorem to find any potential zeros. Again, our rational zero theorem tells us the possible rational zeros are of the form p divided by q, where p are factors of 75 and q is factors of 1. So all possible rational zeros are going to be given of the following form: plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, and plus or minus 25, or plus or minus 75. So now we want to check to see if any of these zeros are actual zeros of our polynomial. So we want to use the remainder theorem to evaluate, along with the factor theorem, which says if we evaluate our function at any of these and we get a 0, then we have a 0 for our polynomial. So let's just go ahead and start. F evaluated at 1 is going to be equal to a 1 minus 3 minus 25 plus 75. This is clearly not equal to 0, so 1 is not a 0. We can go ahead and try f of negative 1, but let's just stick to positives first, and then we'll go to the negative numbers. So we'll try f of 3. This is going to be equal to 3 raised to the third minus 3 times 3 raised to the second minus 25 times 3 plus 75. Here we see that this is going to be equal to 9 minus 75 plus 75, which is 0. And this tells us that 3 is a 0 of f of x by the factor theorem. Or another way to say that is x minus 3 is a factor of our polynomial f of x. So step 3, we want to divide our x cubed minus 3x squared minus 25x plus 75 by our x minus 3. This gives us x minus 3. We'll go into x cubed minus 3x squared minus 25x plus 75. First, we want to get rid of the x cubed, so we're going to multiply our term by an x squared. This gives us x cubed minus 3x squared. Our x cubes cancel out, and our 3x squareds cancel out, and so we're left with a 0 here. Bring down the negative 25x, bring down the 75, and we want to multiply this by a negative 25. So multiplying this by a negative 25, we'll get a negative 25x minus 75, plus 75. So when we multiply that by negative 1, this becomes 0. So this gives us that x cubed minus 3x squared minus 25x plus 75 is going to be equal to x minus 3 times x squared minus 25, which factors out to be an x minus 3 times an x minus 5 times an x plus 5. What we conclude then is that the zeros of this polynomial are going to be x is equal to a 3, it's equal to a negative 5, or a 5. And so these are the solutions to the original equation.